All right, a little recap of what we have done in the last class. It is all about chapter 21, and we are talking about electromagnetic induction. And what I said was, just like any other discovery, this was also an accidental discovery. So Faraday, while he was trying to get the opposite of electromagnetism. So what is electromagnetism? When a current passes through a wire, it produces a magnetic field. So he was trying to get the opposite of that. When you put a magnetic field next to a wire, can a current start flowing in the wire? That's basically that was his search. And in his search, he tried to make a toroid, a coil. He got a core and he put a primary winding on one of them and connected it to a DC cell. So what he did was he took a core, he connected it to a cell, and then he produced a magnetic field through this core. And on the other side, he connected it to a galvanometer, and he found that there was no deflection. And so while he was dismantling this, he detected a deflection, and the deflection was going in opposite directions when he was trying to connect and disconnect. So that's something that he discovered, and then immediately he came to the conclusion that yes, changing magnetic fields can induce a current in a wire. Okay, so that is his discovery, and he came up with the fact that the EMF induced is proportional to the rate of change of flux. Now, what is flux? Flux over area is what we define as a magnetic flux density. Now, this is magnetic field strength, or is also called magnetic flux density. It's the same thing. So how strong are the lines determines how strong the magnetic field is. So this flux for each turn is the product of B and A. So if you know the magnetic field in a certain area, if you know the magnetic field in a certain area to be B, and if you intercept a certain area A, so if you put a coil or something like that over there, how much flux really passes through that coil is BA. Okay? Flux is measured in a unit called Weber. We didn't discuss this in the last class. Flux is measured in a unit called Weber. Unit of flux is Weber, again named after a scientist. And so the flux density, B, is flux per unit area. So Tesla is Weber per meter square. Okay, so we never touched upon these units in the last class. Tesla is Weber per meter square. So if you know the Tesla value of the magnetic field strength in a certain place, and if you know the area in meter square, you can figure out how much flux links a certain area. Okay, so that is the flux. So that is the flux that he was talking about. It is not the rate of change of magnetic field. You can have magnetic field, a weak magnetic field, but you can trap a lot of those magnetic fields through a coil. So it is the rate of change of flux. Yeah. Sam.
What would be the shorthand for the flux unit? Like,
What is
would
shorthand?
be like, I don't know.
Weber, W-E-B.
WEB.
Yeah.
Okay.
W-E-B. That's a shortcut unit. Weber, W-E-B. So Tesla is Weber per meter square. Okay, that's an important thing. Make sure you know this part of it. So the SI unit of flux is Weber. and the SI unit of magnetic flux density is the same as Weber per meter square or just Tesla. Tesla is a more derived unit. Okay, so that was the first thing that he came up with, and he came with this equation: EMF is proportional to d phi over dt. And later on, not later on, I mean, as soon as he came up with this, immediately Lenz investigated more about this induced current's direction, and he discovered something important, and that was Lenz's law. What's Lenz's law? The induced current always flows in a direction to oppose the cause. That is Lenz's law. The induced current, due to the rate of change of magnetic flux, the induced current produced by the EMF is always going to flow in such a direction to oppose the cause. Now, the cause could be the growth of magnetic field, or the cause could be the decay of magnetic field. Whatever may be the case, the induced current will flow in a direction to oppose that cause. So if the growth of magnetic field is taking place, the induced current will make sure that that growth is put down. Okay? So it has to oppose it. Now, if there is a decay of magnetic field, that means the magnetic field is decreasing in magnitude, what the induced current will try to do is to prevent it from decaying. So therefore, Lenz's law. And so the EMF is therefore proportional to minus d phi over dt. The minus sign implies Lenz's law. And the EMF is equal to k d phi over dt. And k takes a value of 1. Which I'll prove later on. K, the value of k is equal to 1. And therefore, EMF is minus d phi over dt. So the EMF induced in any closed circuit or open circuit, the EMF induced produces an induced current, and that is proportional to d phi over dt. Okay. Now, if it's a closed circuit, you're going to get a current. If it is not a closed circuit, you won't get a current. Now, see, this one is not a closed circuit, right? It's open. And so, will there be an EMF here across these two ends? Yes. EMF will be there because there is a rate of change of flux which will cause the EMF. But the EMF will just not be able to do anything until the circuit is closed. When the circuit is closed, then you have the induced current flowing in, right? You understand? Like a cell. If I take a cell and say, does this cell have an EMF? Yes, it has an EMF. Is there a current? No current. When will the current come in? Only when you close the circuit. Current only flows in closed circuits. So unless you close the circuit, even if you have a power source, it's not going to do anything. See, there's power coming out from that outlet. Is there a current coming out? There's no current. Current depends on what you are using it for. And therefore, if you plug something inside and then complete the circuit, then you're utilizing that EMF to make a current flow through. You get it? So when I subject this to a changing flux, then there will be an EMF induced across the tips. But that EMF is not going to produce an induced current, because how can a current flow in an open circuit? So it will produce an EMF. Maybe this side is positive, that side is negative. Or this side is positive, that side is. Depends on which way the flux is changing. Okay. So which way the flux is changing, that will determine whether this is positive, that's positive. And only when you touch it, then it becomes a completely closed circuit. And whenever there is a closed circuit, there will be a current. And especially when you are talking about copper, it's got very little resistance. So even if the EMF induced is 0.001 volt, if there is hardly any resistance, the current can be really high. Current can be high. So the voltage can be very little, but you can have a current that's pretty high. Like for example, if the EMF induced is like 0.1 volt, and with the resistance is 0.001 ohms. This is such a thick copper wire, you can't expect. In fact, it will be still smaller than that, 0.001 ohms. So what will be the current flowing then if I touch it? 100 amperes. So you can have hundreds of amperes going through this thing. And can this take it? Yeah, because look at the thickness of the copper. So 100 amperes going through this wire is possible. But not to this one. This one is a thinner copper wire, and that's not going to take 100 amperes. It will melt. Okay? Now, the other thing that I showed you was this ring. Now, the ring is also something like this, but it's not like this is multiple loops. It's got only one loop, but it's closed. So even if the EMF induced inside here is very little, it's closed and it's a solid conductor, which means the resistance is pretty small. So what will happen when this is subjected to a magnetic field? There will be an induced EMF, which will produce an induced current, which is pretty strong enough. And because the induced current always flows in such a direction to oppose the cause, whatever be the cause, if I show a magnetic north, if I push a magnetic north into it, the current here will flow in such a direction to oppose the magnetic north. So tell me which way. This is the magnetic north. This thing is a magnetic north. If I'm pushing the magnetic north inside the coil like this, the magnetic field is growing in that direction. So what will the induced current do? The magnetic north for this should be this way, because then only you can oppose it. So the current has to flow which way? This way or this way? This way or this way? This way, because you see, right hand grip rule. You get it? So if the north is coming in, the current flows here in this direction to produce a north here. So the north can repel a north. Now what if I bring a south in? If I bring a south in, and how do you oppose a south coming in? To make a south on this side. How do you make a south on this side? The north must be on this side then. So the current has to go this way. All right, you don't see which way the current is going, but you know how it should go. Now, if I have a north pole sitting here, and if I'm trying to withdraw the north pole, I'm trying to take the north pole out, what should this thing do? It should try to oppose my going away. And therefore, if the north pole is trying to go away, this thing is supposed to produce a south pole here and a north pole there. A south pole here and a north pole there. So the current has to go that way. So you should be able to decide which way the current is going to move in a coil. That is a consequence of Lenz's law. And I also stressed on the point that Lenz's law is due to the conservation of energy. Okay, because you cannot produce electric current in a coil from nowhere. Somebody has to do the work. And the work done should be equal to the electrical energy generated. Okay? So electrical energy generated. What's the formula for electrical energy generated or electrical power generated? Let me see if we can get something out. The induced EMF is E, and the induced current is I. What is the electrical power generated? EI. Power, you know the power formula is V times I. So in this case it is E, the EMF, times I, the current. So that's the power. So if I'm changing a flux next to this, it is generating an induced EMF, and therefore as a consequence produces an induced current. Product of those two is the amount of power that is generated by me. How can power be generated without power expended, right? So I have to spend that much power. I have to do that work. So when I push this north in, I'm supposed to be doing that work, because when I push the north in, this is trying to push me back or push me away. So I have to do work against that. So these are things that we discussed in the last class. So if you have an alternating voltage connected on this side, you can expect an alternating current here generated continuously, because this alternating current here will produce alternating flux going both ways. So if the flux is going both ways, the flux is changing continuously, and that means you can expect an induced current continuously flowing in this wire. That induced current is going to always flow in a direction to oppose the cause. That's according to Lenz's law. The induced current that's flowing here is due to an EMF. Sometimes we know, not sometimes, we know that EMF is also called back EMF. It's supposed to be in a reverse direction. You're supplying an EMF here, but this EMF is supposed to be a back EMF because it's supposed to oppose the cause. Yeah.
We're going to get to alternating current.
We will get to it a little bit, yes. Yeah. Alternating currents, yes, we'll get into it. Now the demos that I put up, the first one was this. So yes, so this coil sitting here, yeah, this coil sitting here, and when I plug this into the AC outlet, what we are essentially doing is to provide AC into the first coil, which is this. When I produce alternating currents here, when I send alternating currents here, 110 volts, what happens is the core is going to be magnetized in alternating directions, and this ring is going to be subjected to those changes of magnetic fluxes. So the flux that is produced by the main coil here is going to pass through this little coil, which is this, and automatically there will be an induced current, and that induced current is always going to flow in such a direction to oppose the cause. The cause is this magnetic field. So the magnetic field produced by this one is going to be opposing that at all times, and because of that the ring shoots off because there's a force acting on it as soon as you plug it in. Yeah, that is, once again, need to catch it quickly. All right, so that is the effect of induced current in this. Now the current only went through, current was induced in this for just a little time, and in that little time there was a strong current, but only fractional time, and in that little time there was a big enough force that it took it out. Now if I turn it on continuously, the magnetic field is on always, and you can have this levitating because of that current. So the current that's flowing in this loop is holding it there. Okay? Now it is standing against its own weight. What is supporting it? Weight is acting downward, the magnetic force is pushing it up, so it stays there. Okay? The current induced here is what made this levitate. Okay, so that was magnetic levitation. Now if I force it and keep it here in the high magnetic field area, then the current induced here can be really big enough to produce so much heating effect on the coil. That's something that we did. Who was absent in the last class? Only?
Yeah.
So you're the victim.
Yeah.
You're the first one to take it. Catch it.
Eat. Man. Toss her.
That's-
Get out the kitchen.
It's too hot.
Touchdown pass.
It's not that hot. How did I make it so hot and I send it to you? The first heat was mine. This one, you can see the amount of current that's flowing. I don't want to strip it off. The current that's flowing in here is pretty high, so I'm holding these two terminals. I don't have any problem because I know the voltage is not too much. look at the number of windings here, and look at the number of turns here. So the voltage is stepped down. We'll be talking about transformers after some time. Okay, this is how the transformer works. 110 volts is connected to all these turns. And how much of that is going to come to these few turns? Only a little bit. Maybe 1, 2, 3, 4, 5 volts. And 5 volt is okay for me because I'm not getting a shock with 5 volts. Now, if the voltage goes to 40, 50, 60, then you start feeling the shock. Until then, you're not supposed to be getting much. So even if the voltage is 30 volts, 40 volts, I can touch it and nothing should be wrong. Even if I feel it, it's not going to be regarded as a shock. And in this case, no shock at all, literally, because, I mean, there is shock, but I don't feel it at all because the voltage is very small. But when you touch it, it becomes a closed loop, and the current becomes pretty high. So you saw the sparking there, and the sparking indicates the current is really 20, 30 amperes, for sure. Now, if I put this coil instead,
Your boy couldn't handle it. He could not handle it.
Yeah, so, yeah, this is something that you didn't see last class, right? All right, so what was happening is,
That was cool. It's like jumping.
yeah, this is barely touching now, so occasionally it gets touched, and so immediately the current becomes high. As soon as the current is high, there's a force, and makes it go up, and comes back and lands again, makes a connection, and so on. That is what you saw there. See, nothing is wrong.
Dang it. So sketchy.
The voltage is the kind that we
A little person. Like whatever.
It's not making contact.
Poor guys.
It's not making proper contact.
Yep. I want to see it for the first time. He bounds. He's out. He's like, I got somewhere to be. Uh-oh, he's touching that.
Yeah, that should be good enough.
Come on, baby. Yeah. Oh, you got it! Come on. He can't get off. Oh, tripped.
Tripped.
Dang it.
Okay.
Yeah.
I knew it was going to trip because the wires are getting
So
hot.
close to that stage.
I think I should ask for a
Yeah,
stronger power outlet here. It's hot.
Poor guy.
All right. The other thing that I showed was yes, the electromagnetic induction there. I need a beaker. So this one is connected to a magnetic field, and here, this one is connected to power supply. There's a magnetic field coming up from here, alternating, and there is a coil which is connected to light bulb, and you can see the light bulb coming on without an electrical contact. It's just a magnetic contact. So you can induce a voltage in a totally different coil or wire. So current flowing in one wire induces a current in the next wire. Okay? And I showed that if it is underwater also, it's the same thing. So what's happening is the current is still induced in those wires, produces the potential difference for the light bulb to come on. That's what you see there. What else? Okay. Good. And this is the idea behind the phone chargers. So this is the pad on which we put our phones, and the phone has a coil like that. The phone has a coil inside in that manner, and the output of that coil is connected to your batteries, and so your batteries come on. Yeah.
So like power plants, do they use magnets to induce current to generate power, or how does that work?
In a power plant, that's a different. You need. This is basically the idea of a transformer.
Yeah, I know. I was just asking.
Power plant does not use it. It's not a transformer that's causing it. Power plant uses a generation kind of a technique where you are having a mechanical method of spinning literally a coil, and the coil starts producing a magnetic field, and the coil induces a magnetic field in the next, induces a current in the next wire, and that is what is being generated. So yeah, generator principle is totally a different thing. You can have generators without brushes, you can have generators with brushes. So, just like motors. You can have motor without brushes, you can have motors with brushes. So if there's a motor without brushes, it's mostly using the induced current system. Okay. The other thing I showed was this thing here. That coil, that pipe, the pipe is totally hollow, all right? And this is a cylinder, just like the other cylinder. When I put the first cylinder, it just falls normally under gravity. But I put the second cylinder will be coming down pretty slow. And the reason behind it is that the second one was actually a magnet. Even though it's a magnet, it doesn't stick to it because it's aluminum. So it is not the sticking that is causing it to come late. What is making it come late? Anyone? Anyone, can you explain in your words just how it comes slow? How does it come slowly compared to the other one? The other one comes down fast, whereas this one comes down slowly. How do you explain? Yeah.
A force is created against the cause, so it's going to push it up.
Where's the force coming from?
The force is coming
Yes.
The moving magnet is like the change in flux.
A moving magnet is like the change of flux experienced by this conductor, which is like multiple rings like this. It's multiple rings like this. It's a long ring, right? And so as the moving magnet produces changing flux, this ring induces a current which flows in a direction to oppose the change, the cause. And the cause was the magnets moving in. And so the current induced will always flow in such a direction to prevent it from going down, because that's what causes change of flux. And so it creates a force upward against gravity, but it can't make it stop. Why? Why can't the current make it stop? Why can't the induced current make it completely stop?
Because if it stops, there wouldn't be a change in.
Because if it stops, then the change of flux is gone, and that means there's no more induced current. So it's kind of going down with the terminal speed. Okay? It goes down with the sort of terminal speed. So it depends on the magnet. It depends purely on the magnet. It will just go down according to the terminal speed. So if there's a wire going like that, and the current that in that wire is increasing, and if you have a coil sitting here, a closed coil, increasing current in this will produce an induced current in this in which direction? So you got to use a couple of these rules and then do it. Yes. Yeah.
It's like, what if you put another coil next to that one?
Next to this one,
Does it work like gears? Would it work, or would it have the same?
one will create an effect on the other. Yeah. If you keep one more in parallel like that,
Well, no, I'm saying like put another one like
next to it here.
Yeah.
They will each produce induced currents, and they will have their own magnetic fields. So it'll be kind of complex system. Yeah. So when the current is increasing in this direction, what is happening to the B here? Which way? First of all, decide which way. The current is going down, so the current magnetic field is in. So first decision that you make is which way is the magnetic field it is in. The second thing that you have to think about is what is happening to the B? Is it increasing or decreasing? It's increasing. So what should the induced current do to prevent it from increasing is to produce a magnetic field in the opposite direction, which is not inward but that way. So if you want a magnetic field produced by this current in that direction, which way should the current flow? This way or this way? This way. So the induced current flows like this. You get it? If you think in these lines, you should be able to understand and do it. So again, increasing currents produce increasing magnetic fields in the downward direction, and the induced current will try to prevent it from increasing, and therefore will produce an opposing magnetic field. On the other hand, if it's a decreasing current, it's a decreasing current, meaning going from high to low. What will happen to this coil? First of all, decide which way the magnetic field is. Which way is the magnetic field? Inward. Okay, the magnetic field is still inward. But what is happening to the magnetic field? The magnetic field is going from a stronger value to a weaker value. So in other words, this magnetic field is dying. This magnetic field is dying. And therefore, the induced current will have to oppose that decay of magnetic field. In order to oppose, in other words, in order to stop it from dying, it has to make a magnetic field go in the same direction. Do you get it? Do you get a line of explanation? Decreasing current produces decreasing inward magnetic field, and a decreasing inward magnetic field has to be opposed. So you don't want it to decrease. Therefore, you have to support the magnetic field in the same direction, and therefore the current has to go that way. So that's the induced current. Okay? Any questions on this? You have to use right-hand grip rule pretty much in this very effectively. Right-hand grip rule. Because to determine the magnetic field direction, you need the right-hand grip rule. To determine this current, we still need the right-hand grip rule. All right. Now, let's say we have a magnetic field inward. So there's a magnetic field inward in this region. That's an inward magnetic field. And suppose you have two rails. These are rails. Now, if you have a conductor sitting here, You have a conductor sitting on those rails. Do you understand the picture of the whole thing? You're looking at top down, okay? It's a top down view. So the magnetic field is into the boat, like the magnetic field is right downward, and the two rails are like this, and the conductor is placed on the rails like that. So if the conductor is placed on the rails, are those conductors constituting charges? Is this conductor having charges in it? Free electrons? It's a conductor. Conductor. There are free electrons, right? There are lots of free electrons in this conductor. Now watch. If I pull this conductor to the right, if I forcefully take that conductor to the right along the rails, if I'm going to drag it that way, see what's happening to these electrons. Just think of those electrons as charges, independent charges. So an electron going this way in a magnetic field downward will experience a force. Which way? You understand? Don't look at the conductor as it is. Think of those individual electrons. Take this electron and focus on only that electron. What will happen is, as I'm dragging this conductor that way, the electron is forced to go that way, right? So if an electron is going in that direction in a magnetic field downward, that electron is going to experience a force. Which way? So how do you do it? Since it is an electron going that way, it is equivalent to a current which way? So the current is in that direction and the magnetic field is in. So which way is the force experienced by it? Downward. So what will happen to these electrons if I start dragging this? The electrons will start scooting to this side, right? Leaving this side and this side. That is induced EMF. That's induced EMF. This side is positive, that side is. Do you understand the idea of induced EMF there? But the moment I start dragging it, it's a conductor moving in a magnetic field. So there's a change of flux. And when there's a change of flux, it is inducing an EMF. So that means this side of the rail is positive. This side is, so this side is going to be positive. This side is going to be negative of the rails. So if I keep this conductor here and I drag this conductor and connect this to a voltmeter, that voltmeter will register a voltage. You understand the concept here? Mm-hmm.
Does the use of the word induce mean anything specific?
Induced means like as produced as a consequence. Yeah. Induced. Induction. It's just a consequence. Like if someone is very bright sitting next to you and he does well, you start getting induced to do well. So you start doing well by induction. Okay? It can work the other way around too. If someone is doing poorly and sitting next to you, you start thinking, okay, I'm far better. Therefore, you start going down. So it's possible both ways. So induced is something that's happening because of a consequence. The consequence is this. When I move this conductor, each electron is actually moving that way, and it is a moving charge in a magnetic field. So use Fleming's left-hand rule. Charge electron moving that way is like a current in that direction, and the magnetic field is down, so there will be a force experienced according to Fleming's left-hand rule in the downward direction. So these electrons will scoot to this side, leaving that side relatively positive, and this side relatively negative because more crowding of electrons. Okay? But there won't be any current. There won't be any current yet. There's an EMF though. There is an EMF, positive, negative, but you won't have a current yet. Now, to have a current, you need to have the circuit completed. You have to put a resistor along and connect the circuit, complete the circuit. Yes?
So are the valence electrons going into the bottom rod? Is that what you're saying?
Yeah. The valence electrons are shifting to this side. That's all it's doing. It's just shifting to that side. It can't go anywhere. Yeah.
Wait, I'm kind of confused. So if does the top bar actually like charge change at all, or is it just
It's a
like
conductor, but those are rails like that. So it's like these are two rails, and this is the conductor that I'm moving. These are the two rails. So if you move this conductor that way, what happens to all these electrons? They'll start scooting this way.
Well, yeah, but I'm saying, does that bar's charge actually ever change if, like, you were to take the conductor off?
Which conductor?
Like, when it's going across.
Oh, no.
Would its charge change from that?
If I remove it from there, there's no more potential difference. No. So the potential difference is actually created because you're moving this. Now, of course, when I'm moving this one here, more negative here implies more negative here too, because it's a conductor. And less negative here implies less negative here, because that's also conductor.
So
Yeah.
that's going to create a current on a circuit going clockwise.
The current is going to be clockwise, yes. So as soon as I connect a load there, now it's a closed circuit, right? Can you see the closed circuit? There is an EMF. There is an EMF induced, and the EMF induced is E, produces a current, I, through the resistor, and so you can have a continuous current now. So what is making the current is the electrons going this way. Because as you're moving it, electrons are scooted this way, right? And those electrons complete a circuit, thereby they just keep going to the top and come back again and again. So it produces an induced current in which direction as you move it that way? Downward. No.
Wait, no, it's upward.
No. Induced current upward.
Yeah.
Now, which way should the induced current flow? According to Lenz's law, which way will the induced current flow? In a direction to oppose the cause. What's the cause? You pulling it with a force. You pulling it with a force is the cause of this induced current. Right? Now, why do you say oppose? Now, what is opposing me? I'm pulling it this way. What should oppose me? Is the induced current itself. Did we do earlier? If there's a conductor carrying a current in a magnetic field, it will experience a force. Which law? Which rule? Okay, use Fleming's left-hand rule now. Don't worry about the fact I'm pulling it. Just forget about that. This is a conductor carrying a current upward in a magnetic field downward. So which way will the conductor experience a force? Current is upward, magnetic field is in. Which way is the force? This way. And how much is that force? Formula. BIL. That's a force, right? You know this formula already. That's something that we did earlier. If a current carrying conductor is placed in a magnetic field, it will experience a force. Which way? Left-hand rule, this way. And that is BIL. So if the force is in this direction, how much should I apply as a force? Same thing. If I want to roll this conductor at a constant speed, V. If I want to move this conductor at a constant speed from here to here, if I want to move it like that at a certain speed, that means I need to apply a force exactly the same as the magnetic force acting on this conductor. Is that clear? Make sure you understand each and every little concept. I'll say this all over again. When this conductor is forced by you that way, each electron experiences a force, making this side relatively negative and that side relatively positive, producing an EMF. You won't have a current until you close the circuit. When you close the circuit, there will be a current I produced by this EMF E. In which direction? In that direction. But as soon as the current starts flowing, according to the rules, we know that whenever there's a current in a conductor placed in a magnetic field, it should experience a force equal to BIL. Which way? In this direction. And that is a thing that we are opposed with. So why do you need this application of force? Is to work against that. So this is Lenz's law once again. That is Lenz's law. The induced current flows in such a direction to oppose the cause. What's the cause? Me going this way. And the induced current is trying to oppose that. Do you get it? And so how much is the force that I'm applying here? How much is the mechanical force that I'm putting in? The mechanical force I'm putting in is also BIL. Yes, AJ?
So if you were to just like turn on the middle, would it just shoot to the left first, or would you, in order to get this induced current, you have to move it first?
Only when I move it, this force exists. If I stop it, there is no more induced current. Yeah, it's not going to go by itself or something like that. Yeah.
It's not getting voltage unless you move it.
Because the movement is the cause, the velocity is the cause. So when you're dragging it with this velocity, that's when you have the whole thing happening. So do you understand so far? Now let's look at it from the energy point of view. The energy point of view. Can you tell me how much is the mechanical power that I put in? How much is the mechanical power? Tell me the mechanical power. What's the formula for power? What is the formula for power? Force times? That'll be work. That's work. Huh? No. Force times displacement is work done. And how do you get power? And so what is it then? Force times displacement over time is power. What is displacement over time? Velocity. So FV is going to be the power, mechanical power. So the mechanical power is the force that I put in times the velocity. The force that I put in times the velocity is the mechanical power that I'm putting into the system. Isn't that supposed to be equal to the electrical power generated? Isn't that supposed to be equal to the electrical power generated? The power that I put in is equal to the power coming out. That is energy conservation. Energy is not created nor destroyed. It is only changed from one form to another form. Now, mechanical power that I put in, I spend, is going to be causing this electrical power. Do you get it? How much is electrical power? Formula? Yeah. The electrical power is EI. Now what's the formula for FM? Put it down. So we have BIL times velocity is equal to EI. What do you do from here? I's cancel off. What are you ending up with? We got an expression for the EMF induced in a moving conductor. That's a formula for it. So the formula for EMF induced in a moving conductor is E is equal to BLV. The EMF induced in a moving conductor is B times L times V. The magnetic field strength times the length of the conductor, which is cutting the flux lines, times V. If you know these three things, then definitely there's EMF. What will be the EMF when velocity is 0? Nothing. So if magnetic field is 0, then there's no EMF. So this is an important equation for EMF induced in a moving conductor. So if I have a metal conductor that is moving in a magnetic field, it's supposed to induce an EMF, and the induced EMF is BLV. Now, will that EMF create a current? That depends whether you're completing the circuit or not, right? So whenever there's a change of flux, it's supposed to be inducing this. Now watch this once again. You're not done yet. Now let's use Faraday's law right here. We're going to use Faraday's law. When this conductor is moving from here to here, how much is the rate of change of flux? Okay. So according to Faraday's law, EMF induced is equal to minus K d phi over dt. Correct? And you know what is flux? Flux is B times area. So when this conductor moves from here to here, it is moving V meters every second. So that means our dt is going to be 1 second. So in a time of 1 second, how much is the change of flux? How much is the area? All right, I'm putting that again here. So that's velocity v. Now this will be equal to minus k. Instead of putting d phi, I'm putting d times ba over dt. Or I'll leave it as 1. Okay. If dt is 1 second, if dt is equal to 1 second, what is phi, d phi? Yes?
The area is equal to LV.
The area is L times V, because this side is L and that is V, right? So if the time is 1 second, if dt is 1 second, then the d phi is definitely BA, which is B times LV. You see it? If dt is 1 second, d phi is BLV, because LV is the area. L is the length, V is the distance moved, so the area swept. The area swept by the conductor. How much flux is cut by the conductor? How much change of flux has taken place is that much. And put it down here, you get BLV is EMF. We just proved that EMF is BLV. And now we have Faraday's law telling us that EMF is equal to KBLV. So what's K then? You get it? We just proved without Faraday's law, completely without Faraday's law, we proved EMF is BLV. And now with Faraday's law, we proved it is KBLV. So what is K then? 1. You get it? So K is proved to be equal to 1 through this.
Oh, what do you do about the negative?
Oh, negative is just implying that it is a back EMF. The negative sign only tells you that the EMF is an opposing EMF. You get it?
Yeah.
EMF in the opposite direction.
So does it matter that D5 equals U? So it's that important equation?